All right, ladies and gentlemen, welcome to AP Chemistry with Mr. Kenton. I know that you guys are excited about these videos. I'm excited to put them together for you guys. And as per your request, I'm going to start at the beginning. And we've got some things that I want to cover. This video might be a little bit longer than my other videos because this is review material. These are things that are not necessarily explicitly stated and tested on the AP exam, but they're things that you need to know how to do. And if you go all the way back to the beginning of the year, these were some of the things that we did take a look at. So what we're going to be taking a look at right now is matter and measurement. And again, these are things that are not going to be explicitly tested on the AP exam, but your knowledge and understanding of these ideas is going to be crucial for you to be successful moving forward. So that's why we're going to take a look at them. So if you remember, I'm going to go ahead and just pull up everything. If we had to define what matter is, it's anything that has mass and takes up space. So that means it has to have a measurable mass and it has to have some sort of volume, right? So things like the air that we breathe, the table that I'm sitting at, the chair that I'm sitting in, elements, the water that we drink. These things are all matter because they have mass and they take up space. Now, what we also know is matter is made up of atoms, which is the smallest possible unit of matter that still has the properties and the identity of that element during chemical reactions, right? And then with molecules, this is when you have two or more atoms that are bonded together with a covalent bond. So that could be two or more of the same atom, or it could be two or more different atoms. Here, because we're using the term molecule, that means we're typically dealing with two elements that are nonmetals. You can have your ionic compounds, your ionic bonds that are formed. Those are not called molecules, those are called formula units. But just kind of keep that in mind. And again, this should be pretty straightforward stuff for us. Right, and so here's a particle representation showing you the difference. Obviously, letter A is the only substance there that is an element, and you can see that because element A, oxygen, has only one type of atom. In all of our other pictures, you've got different atom types that are present. In water, you've got the oxygen and the hydrogens. So there's your oxygen, there's your hydrogens. Carbon dioxide, you've got your carbon, your two oxygens, so on and so forth. And that's just giving you a visual representation of the difference between an element versus a compound, or a molecule in this case. Okay, then we've got phases of matter. I know that should not be anything that is new to us, but you've got solids, you've got liquids, and you've got gases. And on the AP exam, a lot of times you're going to be asked to produce particle level diagrams. And so it's going to be extremely important that, like, if they want you to draw a solid, they're going to expect you to draw it like these little tiny packed spheres for your solid. For your liquid, there's going to be less structure, more still compact to an extent, but structure that's there with the ability of the particles to move over each other. And then with your gases, the particles are completely spread apart. There's no connectivity of those particles that are moving around continuously. And so that's just a brief overview of our phases of matter. Again, we ignore plasma because for chemistry, chemical reactions don't typically evolve substances that are in the plasma phase. All right. Now, when you start looking at classification of matter, really matter gets split up into two main types of matter. You've got your pure substances and you've got your mixtures. Your pure substances can then be broken down into elements and compounds. And as we've seen from the previous slides, elements have all the same type of atom, so just one type of atom in an element. Whereas compounds, these are substances that are made from two or more different kinds of atoms, but they must follow the law of constant composition. So for example, H2O has two hydrogens, one oxygen. The law of constant composition says that if you have water, it's always going to form in that ratio. There's not going to be some crazy scenario out there where there's a different ratio of hydrogen to oxygen and that's still water. It becomes a different substance at that point. Now, with your pure substances, it's important to keep in mind that the only way to break down a pure substance any further than where it's already at is that you would have to do some sort of chemical change to it. Thinking of your compounds here, they can be broken down into their individual elements. But then for your elements, the only way they're going to change is if you bind them and bond them with other substances. So those require chemical changes to take place. For your mixtures, that's a different story. So this is your other classification. You've got homogeneous or homogeneous mixtures and heterogeneous mixtures. And so with your mixtures, they're going to be combinations of elements and compounds, but they don't have a specific ratio to them. I want you to think of mixtures can be things like when you buy rubbing alcohol from the pharmacy or you go somewhere and get that, it's a homogeneous mixture because there's an amount of water and an amount of the isopropyl alcohol that's the active ingredient in rubbing alcohol. Okay, now homogeneous just means that it's same throughout. It has identical properties everywhere in the mixture, can also be referred to as a solution. Important for me to mention here, you can classify in terms of what they look like at the particle level of an element and compound. If it's a pure element and a pure compound, you can say that they're homogeneous because they're made up of only the same types of atoms and elements that are there. And if they're pure, there's no other impurities, so then it's not a mixture, right? So you could say that an element is homogeneous. You could say that a compound is homogeneous. But then your mixtures, that's when you would have some combination of two elements or an element and a compound or two compounds that are together. And then you've got heterogeneous, which means that you've got two or more different phases of substances that are present and has the appearance that things are visibly different. That's why they're heterogeneous. And in terms of separating out a mixture, the means of separating out mixtures are through physical means, so it's not going to require chemical processes to separate everything out, right? And here's a flow chart, comes from your textbook, and this can just be a useful tool, some questions to ask yourself as you're analyzing your substance of matter of what does it fit into? Is it a mixture or is it a pure substance? Okay. And again, here's another flow chart looking at the differences between properties. So you've got chemical properties versus physical properties. And again, you've got these things that when you change them, they don't alter the chemical composition. So those are going to be physical properties. These chemical properties, when you change those, you change the chemical composition of your substance. Now, the only thing I'll emphasize here on this particular slide is the intensive versus extensive properties. So remember, intensive properties do not depend on the amount of the substance that you have. It gives you a pretty good list there. But I just think boiling point, melting point, density, it doesn't matter how much of the substance you have. The melting point, boiling point, or density of that substance isn't going to change, right? If you had 10 grams of water or 100 grams of water, the melting point for that water would still be 0 degrees Celsius. Now, extensive properties, those things do depend on the amount of substance that you have. These are things like mass, volume, length, shape. And if you think about it, thinking forward, things like enthalpy, right? The amount of enthalpy that can be produced from a reaction is going to be an extensive property because it's mass dependent. If you have less grams or less moles of it, you produce less heat, or it absorbs less heat. All right, types of changes building on that. So physical changes, just to keep in mind, does not produce a new substance. At the chemical level, the atoms and molecules have not been rearranged in any way, shape, or form. The atoms, molecules, formula units of that substance are still inherently the same. And in general, your physical changes can be reversible pretty easily, and you can do that without having to undergo a chemical reaction of any kind. Whereas a chemical change, like if you look at the bottom, you got water that's being converted into hydrogen peroxide. Clearly, we need another oxygen there in order for that to happen. but you make a new substance. And it's irreversible in the sense that it would require a chemical change in order to take it back to that original state. Whereas with our physical change, we don't have to undergo some sort of chemical change in order for that to happen. I hope that makes sense. Okay, you've got your separation of mixtures. So there are three main methods in which chemists use to separate out mixtures. Now this is important. I know that AP talks about separating mixtures specifically with chromatography, filtration, and distillation. So this is good information to know. So the first one we've got there, that is our filtration or gravimetric analysis. It's where you've got a liquid and a solid, and you are going to, in a funnel, add some filter paper. You're going to pour the liquid in, gradually catch the solid in the filter paper, and allow gravity to push the liquid out into another container so that you can leave behind your solid and determine whatever properties you want to know about your solid, right? You've got distillation. This is really good when you're trying to separate liquids that have differing intermolecular forces. And so in distillation, you heat a mixture, in this case of two liquids, possibly two aqueous solutions, and you heat them, and one substance might have a lower boiling point than the other, and so it gets converted to the gas phase more easily, and it travels and it gets condensed. It passes through this apparatus here where it's cooled and it liquefies again. And so then you've got your two substances that have been separated out. And then lastly is chromatography. And chromatography is when you are taking a look at differences in the intermolecular forces of two solutions or substances that are in a solution or in a dye. And as a solvent moves up the paper, what it does is it causes, based on intermolecular forces, components to separate out that you wouldn't typically see. And so chromatography is, again, really useful and helpful in separating out mixtures when there's a difference in intermolecular forces and polarity, right? So the more polar or the less polar something is, depending on what your solvent is, depends on how much it's going to move up the paper. As you guys are aware, we use SI units in chemistry. Obviously, there's some things that are listed there that are not as applicable to us, but just to highlight, length measured in the meter, symbol is in lowercase m, mass, kilogram, kg, times, seconds, s. Temperature for us is going to be measured in Kelvin. That's going to be particularly useful to us when we're looking at gases and thermochemistry. It's abbreviated with a capital K. And then the amount of substance, the mole, we're all very familiar with that. And then electric current, the ampere, that's going to come up when we look at electrochem stuff much later on. So those are your base units. Those should be pretty familiar to all of us. Now, talking about temperature, these are the conversion factors. I highly doubt that you will have to do any conversions of Fahrenheit to Celsius or Celsius to Fahrenheit, but that Kelvin to Celsius, Celsius to Kelvin is important. And just remember that the conversion is on your reference sheet that you're going to need when you take the AP exam, that you should print off and have with you so you can have that at your disposal. And here it's just trying to show you the temperature changes, the difference in terms of the scales. Obviously, all of those represent the same change in temperature, but then you look at the intervals, and the intervals for Kelvin and Celsius are a little bit smaller than the interval changes for Fahrenheit. Now, for us, we use Kelvin because it's never zero, it's never negative, and so we don't have to worry about weird sign things when we're dealing with Kelvin. Okay. These are just some things that we need to be aware of. Density, mass per unit volume, so grams per milliliter. we use density a lot in our solutions unit. Accuracy refers to how closely a measured value agrees with a correct value. So in a sense, if you're thinking about a bullseye, how close are you getting to that bullseye? And then precision has to do with how closely are your measurements matching up with each other. So obviously in science, our goal is to be both accurate and precise. So just keep that in mind. Significant figures, everybody's favorite. Just as a reminder, these are rules that you need to be familiar with going into the AP exam. Remember, all non-zero numbers are significant. Zeros between non-zero numbers are always significant. So like the number 1005, 1 and 5 would be significant digits. So the zeros in between are also significant. Zeros before the first non-zero digit are not significant. That's a great example there. You've got 0.0003. That has only one significant figure. Those other zeros are just serving as placeholders to get you to the right numerical value. Zeros at the end of a number after a decimal place are significant. So if we had 100.00, because there's a decimal there, and you've got those zeros that are at the end, all of those digits, so 100.00 would have 1, 2, 3, 4, 5 significant digits. And the last one, which can be slightly confusing, is if there's no decimal place and you've got like the number 10,300. Depending on how you record that number, it could have just 3 significant digits, or it could have as many as 5 significant digits. So zeros at the end of a number tend to be a little bit trickier, which is why we use scientific notation to hopefully help eliminate some of that ambiguity in our numbers so we can understand what's significant and what's not. Calculations with sig figs. Remember that when you add and subtract, you want to round your answer to the number that has the least number of decimal places. Okay, so when you're adding and subtracting, you round your answer based on the number with the least number of decimal places. And then when you multiply and divide, you're going to round your answer to the number with the least number of significant figures. Okay, now those rules are different for addition, subtraction versus multiplication and division. That is purposeful. That's not a typo. They're meant to be. And just keep in mind that on the AP exam, you're generally given one additional sig fig, plus or minus 1, as you're doing this. So do your best to try to give the appropriate number of significant figures when possible. Okay, those are the review questions. You should have already done these throughout the year when you guys turned in your textbook problems. But that's the first little intro video that's going to get us started as we make that transition into looking at what is the AP exam looking at with sections 1.1 through the end of that unit. So thanks for stopping by. Hope you find this helpful, and hope to see you guys back here soon.